Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Meteors have long captured the human imagination, streaking across the night sky in brilliant flashes of light. Often referred to as shooting stars, these luminous phenomena are not stars at all, but rather fragments of cosmic material entering Earth's atmosphere at incredible speeds. Their fleeting brilliance and the mysterious origins of these cosmic travelers have inspired myths, folklore, and scientific curiosity for centuries. From ancient civilizations interpreting their meanings as omens, to modern astronomers studying them to unlock secrets of the solar system, meteors occupy a unique place in both human culture and cosmic science. The journey of a meteor begins far from Earth, often in the cold and distant reaches of our solar system. Most meteoroids, the term for the spaceborne rocks before they enter the atmosphere, are remnants of comets or asteroids. Comets, composed primarily of ice, dust, and rocky particles, leave behind trails of debris along their orbital paths. As Earth passes through these trails, tiny particles collide with our atmosphere, producing showers of meteors visible from the ground. Asteroids, which are rocky bodies mainly concentrated in the asteroid belt between Mars and Jupiter, occasionally shed fragments through collisions or gravitational interactions. These fragments may eventually find themselves on a trajectory toward Earth, becoming potential meteorites if they survive the fiery descent. When a meteoroid enters Earth's atmosphere, it encounters the friction of air molecules at astonishing velocities, sometimes exceeding 70 kilometers per second. This friction generates intense heat, causing the meteoroid to incandesce and emit light, creating the bright streak commonly seen from the ground. The glowing path or meteor can vary in color depending on its chemical composition. For example, meteors containing magnesium may appear bright white, while those rich in sodium can emit a yellowish hue. The rapid entry often causes the meteoroid to fragment or explode in the atmosphere, resulting in a fireball or bolide, an especially bright meteor that may momentarily outshine even Venus in the night sky. Not all meteoroids burn completely before reaching the ground. Those that survive the atmospheric passage and land on Earth's surface are called meteorites. Meteorites offer invaluable scientific insights as they represent some of the oldest material in the solar system. Unlike terrestrial rocks, which have been altered by geological processes over billions of years, meteorites preserve their original chemical and isotopic compositions, providing clues about the formation of planets, the early solar system, and even the origins of life. Scientists classify meteorites into three broad categories: stony meteorites, composed primarily of silicate minerals; iron meteorites, rich in metallic iron and nickel; and stony iron meteorites, which contain significant amounts of both rock and metal. Each type tells a different story about its parent body and the conditions under which it formed. Meteor showers are among the most spectacular meteor phenomena observed on Earth. These predictable events occur when Earth passes through dense regions of debris left by comets. One of the most famous annual meteor showers, the Perseids, peaks in August and produces dozens of bright meteors per hour. Another well-known shower, the Geminids in December, is notable for its intensity and brilliant colors. Meteor showers can be both a delight for casual stargazers and a valuable opportunity for astronomers to study the composition and behavior of meteoroids. By tracking their paths and analyzing their light spectra, researchers can infer the chemical makeup of the parent comet or asteroid, deepening our understanding of the dynamic processes in the solar system. The size of meteoroids entering Earth's atmosphere can vary dramatically, from tiny grains of sand to large boulders. Most are small enough to burn up completely, leaving no trace on the ground, while others can cause significant impact events. Throughout Earth's history, large meteorites have struck the planet with tremendous energy, shaping its surface and influencing the course of life itself. The Chicxulub impact, linked to the mass extinction event that ended the age of dinosaurs, is one of the most famous examples, demonstrating the potential power of these cosmic projectiles. Impact craters, some visible from space, are reminders of the planet's ongoing interaction with meteoroids and the dynamic nature of the solar system. Scientific study of meteorites and meteors has evolved significantly with technological advancements. Ground-based observatories equipped with cameras and radar systems allow for precise tracking of meteoroids, enabling researchers to calculate their velocities, trajectories, and possible origins. Satellite-based instruments monitor meteors entering the upper atmosphere, capturing data on their brightness, fragmentation patterns, and chemical composition. In some cases, recovered meteorites are studied in laboratories using advanced microscopy, isotopic analysis, and spectroscopy, revealing intricate details about their mineralogy and the conditions of their formation. These studies not only enhance our understanding of meteoroids, but also contribute to broader questions in planetary science, such as the delivery of water and organic molecules to early Earth. Meteorites have also played a pivotal role in expanding our understanding of the solar system's formation. Some rare meteorites, called chondrites, contain tiny spherical grains called chondrules, which are among the oldest solids formed in the solar system. Studying these ancient grains provides insight into the physical and chemical processes that occurred over 4.5 billion years ago, shortly after the birth of the Sun. Iron meteorites, believed to originate from the cores of differentiated asteroids, offer a glimpse into planetary differentiation, the process by which a planet or large asteroid separates into layers of core, mantle, and crust. Meteorites therefore serve as natural time capsules, bridging the vast distances of space and time to deliver information about the birth and evolution of our cosmic neighborhood. Beyond their scientific value, meteors and meteorites hold a special fascination in human culture. Throughout history, civilizations have interpreted meteor sightings as omens, messages from the gods, or harbingers of significant events. In some cultures, meteorites were revered as sacred objects, sometimes incorporated into religious artifacts or used as talismans. The striking sight of a bright meteor streaking across the night sky evokes awe and wonder, reminding humanity of its smallness in the vast cosmos. Even in modern times, meteor showers inspire public gatherings, stargazing events, and artistic expression, connecting science and culture in a unique and enduring way. Technological advances have also allowed humans to actively study and collect meteoritic material from other celestial bodies. Lunar meteorites, which are rocks ejected from the moon by ancient impacts and eventually landed on Earth, have provided valuable information about the moon's geological history. Similarly, Martian meteorites, thought to originate from the Red Planet, have revealed details about Martian rocks, volcanic activity, and even past water presence. These discoveries expand the scope of meteoritics beyond Earth, emphasizing the interconnectedness of planetary bodies and the movement of material throughout the solar system. The study of meteors and meteorites continues to have practical implications as well. Understanding the frequency, size, and trajectories of meteoroids contributes to planetary defense strategies. Programs that track near-Earth objects aim to identify potential impact threats early, allowing for mitigation strategies to be developed. Even small meteoroids, when traveling at high velocities, can pose risks to satellites, spacecraft, and high-altitude aircraft, making their monitoring essential for space operations. This dual focus on scientific discovery and hazard assessment underscores the multifaceted importance of meteors in both academic and practical contexts. Meteors also highlight the beauty of transient cosmic events. Their fleeting nature, lasting only a few seconds as they blaze across the sky, captures a sense of impermanence that is both humbling and inspiring. Meteor showers, occurring with predictable regularity yet varying subtly each year, encourage people to look upward, fostering a connection with the universe that transcends everyday experience. The interplay of science, observation, and human imagination around meteors exemplifies the broader appeal of astronomy. The pursuit of knowledge, the experience of wonder, and the recognition of our place in the cosmos. Observations of meteors have evolved into sophisticated scientific campaigns, where global networks of observatories collaborate to monitor meteor activity continuously. High-speed cameras and spectrographs capture detailed images and spectra of meteors, revealing the chemical fingerprints of their constituent elements. By studying the light emitted as meteoroids ablate in the atmosphere, scientists can infer the presence of elements like magnesium, iron, calcium, and sodium. each telling a part of the story of the meteoroid's origin and journey. These analyses, combined with orbital calculations, can even identify the parent comet or asteroid from which the meteoroid originated, linking individual meteors to broader celestial structures. In addition to visual and chemical studies, meteors can generate audible phenomena. As larger meteoroids travel through the atmosphere, they compress the air in front of them, producing shock waves that manifest as sonic booms. In some instances, observers report hearing hissing, crackling, or booming sounds accompanying bright fireballs. These sonic effects, while less commonly experienced than the visual spectacle, offer further insights into the dynamics of meteoroid entry and atmospheric interaction. Meteorites, once recovered, undergo meticulous study in specialized laboratories. Researchers examine their structure, mineral content, isotopic ratios, and microfossil inclusions when present. Some meteorites contain pre-solar grains, minute particles that predate the sun and offer a direct glimpse into the interstellar environment from which our solar system formed. Organic molecules found in certain carbonaceous chondrites suggest that meteoroids may have delivered the building blocks of life to Earth, fueling hypotheses about the extraterrestrial origins of prebiotic chemistry. Each fragment, regardless of vitality, carries a wealth of information connecting Earthbound observers to processes that occurred billions of kilometers away and billions of years ago. Meteors also contribute to atmospheric science. The ablation of meteoroids produces trails of ionized gas, which interact with the Earth's magnetic field and upper atmosphere. These trails can persist for minutes and affect radio wave propagation, a phenomenon utilized in meteor burst communications. Studying these interactions helps scientists understand the dynamics of the mesosphere and thermosphere, as well as the distribution of meteoric material across the planet. The continuous deposition of cosmic dust from meteoroids subtly shapes Earth's atmospheric composition over long time scales, illustrating the interconnectedness of cosmic and terrestrial systems. The allure of meteors and meteorites extends beyond professional science into citizen science and public engagement. Enthusiasts around the world contribute observations, photographs, and even recovered meteorites to collective databases, enriching scientific research. Meteorite hunting, while guided by scientific methods, has also become a popular activity, combining adventure, exploration, and discovery. These participatory experiences foster a sense of connection to the cosmos, demonstrating that the study of meteors is accessible to anyone with curiosity, patience, and an eye on the night sky. Throughout human history, meteors and meteorites have left remarkable marks on civilization. Ancient records from China, Babylon, and other cultures describe bright fireballs streaking across the sky, often interpreted as omens or messages from the divine. These early observations laid the groundwork for humanity's fascination with celestial phenomena, inspiring myths, art, and ritual practices. In Europe, meteor showers were sometimes seen as supernatural events, eliciting awe and fear. Even as early as the 16th and 17th centuries, scholars debated the origins of meteors, with some viewing them as atmospheric phenomena and others beginning to suspect their extraterrestrial nature. It was not until the late 18th and early 19th centuries that meteors were scientifically recognized as objects originating from space, a revelation that reshaped our understanding of the cosmos. One of the most dramatic and well-documented meteor events in recent history occurred in Chelyabinsk, Russia, in 2013. A roughly 20-meter-wide meteoroid entered Earth's atmosphere at tremendous speed, producing a brilliant fireball in a shockwave that damaged thousands of buildings and injured over 1,000 people. The Chelyabinsk meteor served as a wake-up call, highlighting the potential hazards posed by near-Earth objects and spurring global interest in planetary defense initiatives. Scientific analysis of the fragments revealed a common type of stony meteorite, offering researchers an opportunity to study meteoroid composition in extraordinary detail. Events like Chelyabinsk underscore that even relatively small meteoroids can have significant impacts, reinforcing the importance of monitoring the skies for potential threats. Famous meteorites have captured both scientific interest and public imagination. The Hoba meteorite in Namibia, for example, is the largest known intact meteorite on Earth, weighing over 60 tons. Its enormous size prevented it from being moved, and it now serves as a landmark and tourist attraction. The Allende meteorite, which fell in Mexico in 1969, is a carbonaceous chondrite that has provided invaluable insights into the early solar system, containing tiny pre-solar grains and organic compounds. Each recovered meteorite tells a unique story of formation, journey through space, and interaction with Earth, linking us tangibly to processes that occurred billions of years ago. Collecting, preserving, and studying these meteorites is a meticulous process, but the knowledge they yield is unparalleled, bridging the gap between astronomy, geology, and chemistry. Meteor showers, meanwhile, continue to enchant observers around the globe. Events like the Leonids, associated with debris from Comet Tempel-Tuttle, can produce spectacular meteor storms with hundreds or even thousands of meteors per hour. Meteor showers occur at predictable times of year, allowing stargazers and researchers alike to anticipate their arrival. The experience of watching a meteor streak across a dark sky, perhaps accompanied by a trail of glowing dust, is not merely aesthetic but also educational. Amateur astronomers often participate in monitoring meteor showers, recording sightings and contributing data that helps scientists track meteoroid populations, their velocities, and orbital paths. The interplay between casual observation and professional study illustrates how meteors connect everyday human experience to cosmic processes. Space missions have further deepened our understanding of meteors and their origins. Missions like NASA's Stardust collected dust from Comet Wild 2, bringing microscopic samples back to Earth for laboratory analysis. Japan's Hayabusa and Hayabusa 2 missions successfully returned samples from asteroids at Tokawa and Ryugu, respectively, providing pristine material to study processes that occurred at the dawn of the solar system. These missions demonstrate that meteoroids are not just transient lights in the sky, but also messengers carrying fundamental information about planetary formation, organic chemistry, and the distribution of water and other volatiles in space. Analyzing these extraterrestrial materials allows scientists to construct models of how planets formed, how life-essential elements were delivered to Earth, and how future space exploration might utilize asteroid resources. Meteorites also offer insight into extreme environments in space. Some contain minerals that only form under high pressure or high temperature conditions, revealing violent collisions in the early solar system. Iron meteorites, believed to originate from the cores of differentiated asteroids, contain metallic structures called Widmanstätten patterns, which form over millions of years under slow cooling conditions. Stony iron meteorites, with both metallic and silicate components, testify to processes that mix molten cores with surrounding rock, illustrating the complexity of planetary differentiation. By studying these materials, scientists can reconstruct histories of parent bodies, infer their sizes, internal structure, and even the processes that led to their fragmentation and eventual journey toward Earth. The role of meteorites in the origin of life is an intriguing and active area of research. Certain carbonaceous chondrites contain amino acids, sugars, and other organic molecules, suggesting that meteoroids could have delivered prebiotic materials to early Earth. This concept, known as panspermia, proposes that life-essential compounds were distributed across the solar system via meteorites and comets, potentially seeding planets with the ingredients for life. Experiments simulating meteoroid entry have shown that some organic molecules can survive the intense heat of atmospheric entry, lending credibility to the idea that cosmic material contributed to the chemical precursors of life. If true, meteors are not only spectacular light shows, but also participants in the grand story of life's emergence on our planet. Meteorites are not limited to Earth's past. They continue to shape our understanding of the present solar system. Studying micrometeorites, tiny particles that settle on Earth's surface from the upper atmosphere, allows researchers to track the ongoing influx of cosmic material. Antarctic ice and deep-sea sediments serve as natural collectors, preserving these particles for analysis. The chemical composition, isotopic ratios, and mineralogy of micrometeorites provide a continuous record of meteoroid populations, helping scientists monitor changes in cometary and asteroidal debris streams over time. This long-term perspective offers valuable context for understanding both the frequency of meteor showers and the broader dynamics of the solar system. Meteorites have inspired cultural, artistic, and educational endeavors around the world. Museums frequently display meteorites alongside explanatory exhibits, allowing the public to touch or observe fragments of extraterrestrial material. Artworks and literature often draw on meteors as symbols of change, transience, and cosmic connection. Public meteor watching events bring communities together, offering educational workshops, night sky tours, and discussions of planetary science. These experiences blend scientific understanding with human curiosity, emphasizing that meteors are not only objects of study, but also sources of inspiration, wonder, and imagination. Looking to the future, meteors and meteorites hold practical and strategic significance for humanity's expansion into space. Understanding meteoroid streams is critical for spacecraft design, mission planning, and planetary defense. Potential resources contained within asteroids, metals, water, and other volatiles, could support space-based industries, fueling exploration and settlement. Emerging technologies in asteroid capture, resource extraction, and even deflection of potentially hazardous meteoroids underscore the growing importance of meteors beyond their aesthetic and scientific value. They are not merely celestial fireworks, but also participants in humanity's future as an interplanetary species. Meteor science also intersects with education and outreach. Schools, universities, and planetariums utilize meteors to teach concepts in physics, astronomy, chemistry, and geology. By observing meteor showers, students learn about gravity, orbital mechanics, atmospheric friction, and energy transfer. Hands-on experiences, such as identifying and analyzing meteorites, provide tangible connections to abstract scientific principles, reinforcing learning while nurturing curiosity. Public engagement initiatives, ranging from meteorite hunts to citizen science observation campaigns, cultivate a deeper appreciation for the cosmos, encouraging the next generation of scientists, explorers, and dreamers. The dynamic interaction of meteoroids with Earth's atmosphere exemplifies broader astrophysical processes. Meteors are natural laboratories for high-temperature chemistry, plasma physics, and shockwave propagation. Their luminous trails provide information about atmospheric density, composition, and temperature at high altitudes. Tracking meteor trajectories informs our understanding of orbital mechanics, resonances, and perturbations caused by gravitational influences from planets and other celestial bodies. Meteors connect multiple fields of study, from planetary science and astronomy to physics and geochemistry, highlighting their interdisciplinary value and scientific richness. Ultimately, meteors and meteorites are more than transient phenomena. They are messengers from the cosmos. Each streak of light across the night sky tells a story of cosmic origins, interplanetary journeys, and interactions with our planet. Each meteorite fragment embodies billions of years of solar system history, offering scientists an unparalleled record of planetary formation, collision, and chemical evolution. The awe-inspiring spectacle of a meteor shower and the tactile reality of a recovered meteorite converge to remind humanity of its connection to the universe, the fragility of our planet, and the richness of the cosmic story unfolding beyond our atmosphere. The study of meteors continues to evolve, fueled by curiosity, technological innovation, and a desire to understand our place in the cosmos. New missions, improved observational networks, and advanced analytical techniques promise deeper insights into meteoroid origins, compositions, and interactions with planetary bodies. As we continue to explore, predict, and interpret these cosmic visitors, meteors will remain both a scientific resource and a source of wonder, bridging the gap between Earth and the vast universe beyond. They are celestial storytellers, painting the night sky with fleeting brilliance, whispering secrets of creation, and inviting all who look upward to ponder the mysteries of the cosmos. Meteors remind us of the scale and dynamism of the universe, connecting human experience to processes that span billions of years and billions of kilometers. They are fleeting yet enduring, beautiful yet informative, dangerous yet enlightening. From ancient myths to cutting-edge space missions, from spectacular meteor showers to recovered meteorites studied in laboratories, these cosmic snowballs continue to shape human understanding, culture, and imagination. In every glowing streak across the night sky, in every fragment lying on Earth's surface, Meteors carry the story of the universe, waiting for those who seek to unravel their mysteries. In addition to their scientific and cultural significance, meteors have played a pivotal role in shaping human imagination and art. From ancient petroglyphs depicting streaks across the night sky to modern literature and cinema, portraying fiery objects from space, the visual drama of meteors has inspired generations. Artists have captured their brilliance in paintings and illustrations, while writers have used meteors as symbols of sudden change, destiny, or cosmic connection. The striking imagery of a bright meteor streaking through the heavens evokes a universal sense of wonder, transcending cultural boundaries and connecting people to the shared experience of observing the night sky. In a world increasingly illuminated by artificial lights, meteors remain one of the few natural phenomena that remind us of the grandeur and scale of the universe. Meteorites themselves have a unique allure that goes beyond aesthetics. Collectors and researchers prize them not only for their rarity, but also for the tangible connection they offer to other worlds. Unlike any terrestrial rock, a meteorite is a direct piece of space, having traveled millions or even billions of kilometers before reaching Earth. Some meteorites, known as lunar or Martian meteorites, carry the signatures of entire planets, revealing the geology, volcanic activity, and history of celestial bodies far from our own. Holding a meteorite in one's hand is like holding a fragment of cosmic history, a physical reminder of the dynamic and interconnected nature of the solar system. The study of meteorites also provides insight into the violent processes that shape planetary systems. Collisions between asteroids and other celestial bodies produce fragments that travel through space, sometimes crossing Earth's orbit. These collisions are not only destructive, but also constructive, mixing materials from different parent bodies and redistributing them throughout the solar system. By studying meteorites, scientists can reconstruct these ancient collisions, understanding how matter was redistributed, how planets evolved, and how certain chemical elements became concentrated in specific regions. Meteorites, therefore, are not passive visitors, but active participants in the history of the cosmos. Technological innovations have expanded our ability to observe and study meteors in ways unimaginable just a few decades ago. High-resolution cameras, radar systems, and spectroscopic instruments now allow scientists to capture every detail of a meteor's descent. These tools reveal subtle nuances of light emission, fragmentation, and chemical composition, enabling precise reconstruction of the meteoroid's trajectory and original orbit. Networks of observatories across the globe collaborate to track meteor showers, fireballs, and sporadic meteors, sharing data in real time. This global effort not only improves scientific understanding, but also enhances public engagement, as enthusiasts and researchers alike witness the fleeting brilliance of meteors together, bridging the gap between professional astronomy and citizen science. Meteorites have also fueled advancements in planetary defense. Understanding the ways, composition, and trajectories of meteoroids is critical for assessing potential impact risks. Early detection and trajectory modeling allow scientists to predict potential collisions with Earth, providing time to implement mitigation strategies if necessary. While most meteoroids are small and harmless, large impacts, such as the one that contributed to the extinction of the dinosaurs, illustrate the potential consequences of unanticipated collisions. Studying meteorites and monitoring meteoroid populations, therefore, not only satisfies human curiosity, but also serves a practical purpose, safeguarding our planet and preparing humanity for potential cosmic hazards. The interplay between meteors and Earth's atmosphere continues to reveal fascinating scientific phenomena. As meteoroids burn through the upper atmosphere, they create ionized trails that interact with Earth's magnetic field, producing subtle changes detectable by radar and radio instruments. These trails can persist for minutes, serving as natural laboratories for studying high-altitude physics, plasma behavior, and atmospheric chemistry. Meteor showers, by producing predictable and concentrated trails, offer scientists a unique opportunity to study these interactions systematically, revealing the delicate balance between cosmic and terrestrial forces that shape our environment. Meteorites have also become powerful tools for understanding time itself. Radiometric dating of meteorites provides precise estimates of their age, revealing the timing of processes that shape the early solar system. Some meteorites contain ancient inclusions that predate the formation of Earth, offering a direct glimpse into the primordial cloud of gas and dust from which our planetary system emerged. By studying these time capsules, scientists can reconstruct the chronology of planet formation, collision events, and chemical evolution, deepening our understanding of the solar system's history and our own origins. Each meteorite, therefore, is not merely a rock, but a historical document written in stone, bridging the vast scales of time and space. Meteor science is also increasingly interdisciplinary, integrating astronomy, geology, chemistry, physics, and even biology. Organic compounds in certain meteorites suggest that the ingredients for life may be widespread in the cosmos, inspiring research in astrobiology and the search for life beyond Earth. High-energy impacts observed in craters and meteorite studies inform models of planetary formation and surface evolution. Spectroscopic studies of meteors reveal the distribution of elements across the solar system, contributing to theories about planetary differentiation, chemical gradients, and material transport. The study of meteors, therefore, is a gateway to understanding the broader processes that govern not only Earth, but also the universe as a whole. Meteorites have inspired stories of human adventure and discovery. From expeditions to Antarctica in search of pristine meteorites to desert hunts in Namibia and Australia, enthusiasts and scientists alike travel to remote and harsh environments to recover cosmic fragments. These journeys often combine science, exploration, and discovery, producing narratives that captivate the public imagination. The thrill of unearthing a meteorite, knowing it has traversed interplanetary space to reach the Earth, embodies the human desire to connect with the cosmos and understand our place within it. Each recovered meteorite carries with it a story of origin, journey, and discovery, intertwining the vastness of space with human curiosity and perseverance. Meteor showers, meanwhile, provide shared experiences that unite communities and cultures. Whether it is families gathering in backyards, students observing from school grounds, or entire cities organizing public viewing events, the spectacle of meteors evokes a sense of connection across generations and geographies. Observing a meteor streak across the sky can inspire questions about physics, chemistry, and cosmology, fostering curiosity and learning. The universality of the experience, anyone, anywhere, can look up and witness a meteor event, creates a powerful link between individuals and the broader universe, reminding humanity of both its smallness and its capacity for wonder. Looking toward the future, meteors and meteorites are poised to play an increasingly important role in space exploration and resource utilization. Asteroids, the progenitors of many meteorites, contain vast stores of metals, water, and other materials that could support long-term human activities in space. Plans for asteroid mining, planetary defense, and interplanetary travel all rely on a deep understanding of meteoroid properties, composition, and trajectories. By studying meteors and meteorites, scientists not only satisfy a quest for knowledge, but also prepare humanity for a future in which our survival and expansion may depend on harnessing resources from beyond Earth. Meteors, in this sense, are both messengers from the past and keys to the future. Ultimately, meteors and meteorites embody the intersection of science, culture, and imagination. They remind us of the vastness and dynamism of the cosmos, the fragility of our planet, and the deep connections between Earth and the wider solar system. From the fleeting streak of a shooting star to the enduring presence of a recovered meteorite, these cosmic phenomena inspire wonder, inquiry, and exploration. They are natural storytellers, carrying the narrative of the universe across space and time, inviting humanity to observe, understand, and dream. The brilliance of a meteor cutting through the night sky, the intricate patterns in a metallic meteorite, the chemical signatures preserved in ancient rock fragments. All these elements converge to tell a story that spans billions of years and countless kilometers. Meteors are both transient and enduring, ephemeral yet timeless, captivating the human imagination while providing profound scientific insights. In observing, studying, and celebrating meteors and meteorites, we participate in a cosmic dialogue, one that links our lives to the history of the solar system and the ongoing dance of celestial bodies. They are luminous reminders of the universe's grandeur, the mysteries that await discovery, and the enduring human desire to explore the heavens.